Good afternoon, everybody. My name is Lucian, and today I will be your tutor for this Yebo Physics session. And today we'll be covering a very nice topic in dynamics called torque. Okay. But before we go with torque, let's just go up a bit first to equilibrium. I know you've done equilibrium with Arnold or Zola, either of them, but let me just restate what equilibrium is in 14.2. Okay, this is for both PHYV and for FVV. Okay, now equilibrium, what is it? Now most of you have like an intuition of what equilibrium is. It's when it's in stable form, nothing is moving, or there are no net forces acting on something. That is in equilibrium. Okay, it's more or less at stasis. Okay, now equilibrium is defined to be motion without linear or rotational acceleration. So your intuition would have been right. It's something where there's no net force, and if there's a net force there must be an acceleration. So equilibrium, what is equilibrium? There it is there. Equilibrium is defined. This is the actual definition of equilibrium. So equilibrium is defined to be motion. Equilibrium is defined to be motion without linear or rotational. So because now you have done both linear and rotational acceleration. So equilibrium is defined to be motion without linear or rotational acceleration. The definition is right there. You can just pause it. I just wrote it down so that you can actually see it better. So equilibrium is defined to be motion without linear or rotational acceleration. Okay, moving on to today's topic, torque. Okay, now in this introduction here, they say in the previous chapter we introduced the concept of torque to quantify the effectiveness of a force in a rotating object. In rotating an object. Okay, so torque is the rotational equivalent of a force. Please, that is very important there. Okay, I'm going to just note some important points. Okay, so torque, that is equilibrium, we already defined it. So torque, an important concept of torque, just torque is, oh, let me just write it on that clean page. Torque it's 14.3. torque. Okay, so number one, torque is the rotational equivalent of a force. So torque is the rotational equivalent of a force. Okay, just as we have force that are acting in straight lines, torque would be the rotational equivalent of a force. So far we've only done forces acting in straight lines. Okay, you can break it up into components, but it is still just acting in straight line, that force. Okay, we haven't done any curved forces. Okay, at no point have we done a force that is curving. Okay, so torque is just the rotational equivalent of a force. It's a force acting on a curve. Okay, in this case, in a rotating manner. Okay, so torque is just the force acting on a curve, acting in a curve, or in the direction of a curve. Okay, so it's the rotational equivalent of a force. Okay, so torque is just the force acting in a rotating manner or causing something to rotate. It is a measure of the effectiveness of a force in inducing rotational acceleration. So torque causes angular acceleration. So torque causes angular acceleration. Now consider the figures below. They say the net external force on the stick in both scenarios is 0. Okay? The net external force is 0. But in one case equilibrium is achieved, that is the first one, whereas in the other, with the same forces applied in different places, the stick experiences accelerated rotation. Therefore, we know that the point at which a force is applied is another factor in determining whether or not equilibrium is achieved. Okay, so where you apply the force can determine whether equilibrium is achieved or not. Now, another thing about torque, the SI units for torque is the Newton meter. Okay, that is the SI units for torque. And torque has two directions. Okay, two directions. It can be clockwise or it can be counterclockwise or anti-clockwise. Okay, the book says counterclockwise, so we'll go with that. Counterclockwise means opposite to the direction in which the hands of a clock would move. Counterclockwise. Those are the two directions of torque. Torque is SI units of Newton meters, and it has two directions, clockwise and counterclockwise. Okay. Now they say to understand what factors affect rotation, let us think about what happens when you open an ordinary door by rotating it on its hinges, which is its pivot point. Identify three factors that determine how effective you are in opening the door. Okay. How does this correlate with the equation for torque? Okay. Now, three factors that determine how effective you are in opening a door. Let's just think about that for a moment. Okay. Let's say these are the hinges for this door. This is the actual door. These are the hinges. This is the door. We're looking at it from above, okay? And the door swings open that way, okay? Door swings open that way. Okay? So you open the door here. Now, what factors affect the rotation? Obviously, the force that you apply, okay? Obviously, the force that you apply, okay? A factor that determine how effective you are in opening the door is the force you apply. That's a factor. Force you apply. Another factor that determines how effective you are in opening the door is where you apply the force. Okay, of course, you must apply force to open this door. Okay. And then, of course, you must know where to apply the force. Okay, because if you apply it at the hinges, it's not going to move much. Okay, it might, but not much. Okay, if you push it directly on the hinges, it's not going to move at all. Okay, where you apply the force and number three, another factor that would affect how you open this door is in what direction you apply the force. Those are three factors that can influence how effective you are in opening this door. In what direction you apply the force. Now those are three that come to mind quickly when I'm thinking about opening a door. Okay. And how does this correlate with the equation of torque? Now we haven't done the equation of torque yet. We will get to it now. Now the equation of torque is as follows. Okay. Torque, represented by the Greek symbol tau, is equal to the force acting perpendicular on some object acting perpendicular to the object multiplied by the distance or the length of that object. Okay, I hope that makes sense. The torque is just a product of the force or the perpendicular component of the force multiplied by the length of that object, d. Okay, that is how you calculate torque. Okay, how you would go about calculating torque. Okay, now let's say when opening a door you push on it perpendicular. Let's put this formula into use. Okay, I have several problems here, examples, but let's first do this example here and then we can do some others. Okay, so first, the example problem number 2 says when opening a door. Okay, so let's draw that door we just drew. Those are the hinges or the pivot. This is the door. Okay, you open this door this way. You open the door like that. Okay, so you open this door in that direction. Now they say when opening a door you push on it perpendicular. Okay, so you push on it, the angle of the force, the angle that the force makes with the door is perpendicular on 90 degrees. Okay, so and the force is 55.0 newtons at a distance let's say 0.85 meters. Okay, so this distance here that this force is acting from the hinges is 0.850 meters. Okay, so the distance 0.850 meters. Now torque, we've already established, is just a product of the perpendicular component of a force multiplied by the distance at which that force acts on that object. Okay, so the perpendicular component of this force, since it's already acting perpendicular, it is just going to be the force given, which is 55.0 newtons, multiplied by, you'll now see why the units of torque is newton meters, and the distance, it's acting at a distance of 0.850 meters. Okay, so the units is going to be newton meters. Okay, so newton meters. Okay, now 55 times 0.85, so just 85% of 55, something in the 40s. We say that it's 46. Okay, let's see. Always make sure. Let me just check. 55 multiply. Now I have a lot of other problems. I didn't do this one for obvious reasons, but I wanted to do it with you because the answer is already there. I just want to make sure that the book is spot on. 0.85, the answer is already there, and there you have it. It is 46.75. okay, so it is correct. The book is correct, so it is 46.75. Where's the notes? Yeah, there we go. So the answer is 46.75 newton meters. Okay, now you can just, in this case, in our case here, this would be counterclockwise. Okay, in our case it will be counterclockwise. because of the way I drew this door. Okay, I drew it like that. So that will be counterclockwise. We will come to equilibrium problems in a minute. Okay, let's do some more problems regarding pure torque. Okay, just so that we get a feel for it. Okay, there is torque, but there is only that one problem on torque. Okay, let us get into some more problems regarding torque. Okay, this is problems that I have found online and in other textbooks. Let me just rather write it on the clean page. These are some example problems I found in other textbooks like Sauer and Jewett, Halliday and Resnick, Sauer and Vail. They're all textbooks for physics. Okay, so this is problems. Let's see. Okay, so I'm going to draw most of these situations. This is the pivot. Okay, that is the pivot point. We have some object and we have a force pulling this object in that direction, and that force makes an angle of 30 degrees with this object, and this force has 5 Newton unit. Okay, so they want the torque. Okay, what is the torque? Now, first of all, we know the torque is nothing but the product of the perpendicular component of the force multiplied by the distance at which this force acts. Okay, so the perpendicular component of this force, you would calculate it's going to be that there. That's going to be the perpendicular component of this force. So it's going to be the sine. Okay, so it's going to be the sine of 30 multiplied by 5. That's going to be the give you a perpendicular component of this force. Sine of 30 multiplied by 5 newtons. It's going to give you the perpendicular component of this force multiplied by the distance at which this force acts, which I did not put in. It acts at a distance of 4 meters. Okay, this force acts at a distance of 4 meters. Okay, so multiplied by 4 meters. Now that's going to give you an answer of the sine of 30 is a half. A half times 5 is 2.5. 2.5 times 4 is 10 Newton meters. So there you have it. The torque caused the torque on this object around this specific, that is the pivot, by the way, that is the pivot point. This 5 Newton force acting on this object, linear object, at 4 meters away from its pivot point. Okay, you can envision this as maybe a door, and these are the hinges. Okay, it doesn't have to be a door, it can be anything, but as long as it's on a pivot, acting on that pivot point and at a distance 4 meters with a force of 5 newtons at an angle of 30 degrees with the door. Now we must always use the vertical component, or the component perpendicular to the component of the force that acts perpendicular to the object on which it acts, the force, on which the force acts. Okay, now I hope that is clear. We're going to do just a bunch of them and then move on to equilibrium, and then after equilibrium we will go to the next. Let's just call this one number 1, and we will go to the next problem and the next and the next, and we'll go to equilibrium and then some other problems. Okay, so problem number 2. Okay. Problem states as follow. It is a word problem. How much force, says how much force would Joe how much force would Joe have to apply? So how much force would Joe have to apply perpendicular? How much force does Joe have to apply perpendicular to create a torque, to create 550 Newton meters of torque so we need to calculate the force needed to be applied perpendicular to create 550 Newton meters of torque 0.20 meters away from the pivot point. Okay, so I'm going to from away from the bolt he is trying to loosen. Okay, so this is the situation with Joe. He is creating, let's say he's using a ratchet spanner. Okay, this is the bolt, or let's just draw a normal spanner. That will be easier. Okay, so let's say that is it. There's the spanner. Okay, and Joe is trying to loosen this bolt with the spanner. Okay, they ask how much force does Joe have to apply perpendicular. So we want this force that Joe needs to apply if he's creating a torque of 550 newtons, about 0.2 meters. So this would be then be the distance this force would be acting is 0.2 meters, so 20 centimeters away from the bolt. Okay, he's applying the force there. So let's see. Okay, we know that torque is equal to the perpendicular component of the force multiplied by the distance at which that force acts. Now, in this case, therefore, if we rearrange that, we can get that the perpendicular component of the force is equal to the torque divided by the distance at which this force is acting. Okay, so therefore, the perpendicular component of the force is just going to be equal to the torque in this case, which is 550 Newton meters, divided by the distance of 0.2 meters, is going to give us a force of 2,750 newtons. Okay, so a force of 2,750 newtons acting at a distance of 0.2 meters will bring about a torque of 550 Newton meters. Okay, so the torque is equal to the perpendicular component of the force multiplied by the distance at which that force acts. Okay, now if we rearrange that, we find that the perpendicular component of the force is equal to the torque divided by the distance at which that force acts. Okay, now if we substitute in the given torque and the given distance, we get that 550 divided by 0.2 meters is equal to 2,750 newtons of force. Okay, so say 2,750 newtons of force will acting at a distance of 0.2 meters perpendicular to the spanner would bring about a torque of 550 Newton meters. Okay, so that is a problem in just basically the problem was in substitution, because you know now the formula for torque. Okay, next problem, okay. Problem number 3. Good example always to use is that of the spanner, okay, because you are applying a force to bring about a torque. This is a situation, okay, this is a fulcrum or the pivot point. This is some sort of beam attached to that pivot point. This is a force acting at that point at the end of this beam. We're looking at it from above. Let's say this is a door. Let's call it a door. Okay, so those are the hinges then. Let's just call that then the hinges. Those are the hinges of the door. And this force is acting at a distance of 0.45 meters. They want to calculate the torque created by this force, okay, if that force is 100 newtons. Okay, so these are the hinges. Sorry, let me just redraw that. That is just pointing to the hinges. So the torque is equal to the perpendicular component of this force. It's already acting perpendicular times the distance at which it acts. In this case is 0.545 meters, so it'll be 100 newtons multiplied by 0.45 meters. And of course in this case it's going to be rotating this thing clockwise. Okay, so it doesn't have to be clockwise. The force could have been acting from underneath. It's just how I drew it. So it's going to have, since it is a vector after all, it is going to have a clockwise direction. Okay, so 100 times 45 is just 45 Newton meters. Okay, there you have it, 45 Newton meters. Now the next problem I'm going to put out, let me just see if there are no one yet. None yet, but I'm hopeful. Okay, so let's continue with talk. Next problem. Now of course these are not problems in your book because the workbook does not have many problems on talk. These are my own problems. Okay, number 4. Okay, I know I use numerical Roman numerals to mark number 1 and 2, and now I'm using actual numbers for number 4, 3 and 4. It's not really a matter, no big deal. So the next thing, we are given a situation, we need to calculate the torque. Let me just draw the situation. So we are given a, just ignore my ugly bolt. It's supposed to be a bolt, by the way. It's very ugly, I know. This is supposed to be a spanner. It's supposed to be. I have zero artistic talents. Okay, so there we have a spanner trying to loosen a bolt. Okay, It is a terrible drawing, but we are not interested in the drawing at the moment. We are interested in the problem it provides us. So it acts at a distance of, it's acting at a distance of 0.28 meters. And the force acting on the spanner is being applied at an angle, right? An angle to the perpendicular, and that angle is 30 degrees. That force is being applied, so 60 degrees from the horizontal but 30 degrees from the perpendicular. And finally, the force being applied is 250 newtons. Okay. So I want to loosen this bolt. I'm applying a force of 250 newton at an angle of 30 degrees from the perpendicular at a distance of 0.28 meters, okay, so 28 centimeters away from the bolt. Now, what is the torque created in this situation? That we know torque is just nothing but the perpendicular component of the force multiplied by the distance at which the force acts. The perpendicular component of the force in this case, if we calculate that, perpendicular component, it's going to be, let's see, that's going to be the triangle. Let's draw the triangle. This is going to be 30, okay, that's going to be 60, that's 90. So we want that's going to be adjacent to the 30 degree angle, okay? So it's going to be cos, so the cos of 30 degrees multiplied by the force of 250 newtons multiplied by 250 newtons is going to give you a perpendicular component of the force multiplied by the length or the distance at which this force acts, which this perpendicular component of the force acts, which is 0.28 meters. Okay, and that's going to give me a torque of 61 Newton meters. Of course, first you can just actually calculate the perpendicular component of the force. Okay, the cos of 30 multiplied by 250 is just 216.5 newtons. It's 216.5 newtons. That's the perpendicular component of the force multiplied by the distance. Now 28% of that is just equal to 61 Newton meters. 61, so it's almost a third. A third, yes. 61 Newton meters of torque. In this case, since it's pushing it down, it's going to be a clockwise direction. Okay, clockwise or CW. Okay, I hope everyone understood that problem. Okay. Let's continue. The next problem. I'm going to draw it, and mostly going to be drawing a lot of them. The next few deals with multiple forces where the fulcrum is in the middle. Okay, the fulcrum will be in the middle in the next two problems. Okay, now we always measure the distance from where the force acts to the fulcrum. Okay, so let's see. We have a distance. There's the fulcrum, just right here, fulcrum. This is the fulcrum there. Right? Then we have a box number 1. We have box number 2. Okay, let me just redraw this. Okay, we have the fulcrum there. That's going to be the fulcrum or the pivot point. Okay, then we have box number 1, box number 2, and box number 3. Number 3, number 2, and number 1. So we have 3 boxes. Okay. Now each of these boxes are have a weight, so they're pulling down with a force. The first one is pulling down with a force of 19.6 newtons. The second one with a force of 9.8 newtons. Okay? The third one with a force of 4.9 newtons. Okay, 4.9 newtons. Okay, they want us to find the sum. Okay, now there's something I almost missed to give you the distances. Okay, so the first distance from box number 1 to it is 0.2 meters. I'm not going to write in meters, I'm just going to write in the numerical values. It is in meters. It is 0.2 meters. The second one is to box number 3, it's 0.3 meters. And the last one is to box number 1. It is 0.4 meters. Okay, so the distance is measured from, you can see, from the fulcrum to where the force is acting. Okay, to where the force is acting. In these cases, all of them, the forces are acting perpendicular to the beam or the seesaw situation. Okay, so it's perpendicular component of the force. It's already acting straight down, perpendicular to the object it's acting on. Okay, so it's already working with the perpendicular component of the forces. Okay, so we want the sum of the torques. What is the sum of the torques? Okay, now we know to get the sum of the torques is going to be equal to the torque from box 1, the torque caused by box 1, the torque caused by box 2, plus the torque caused by box 3. Okay, now before we begin, let's just pick a positive direction. Okay, so let's take clockwise as positive. Okay, so let's say clockwise is positive. So all the clockwise torques, all the forces that causes a clockwise torque is going to have a positive in front of it. The rest will have negative. Okay, so clockwise torque. So which of these torques would cause it to rotate clockwise? Okay, this force would cause it to rotate clockwise. It's only number 3. So torque number 3 will have a positive in front of it, while this one will cause an anti-clockwise torque, while this one will also cause an anti-clockwise torque. So they will have negatives in front of them. Okay? So T1 and T2 will have negatives in front of them. Okay. Now, of course, torque number 3, you know very well that torque is just force, perpendicular component of the force, which is 4.9 in this case, multiplied by the distance at which that force acts. It is 0.3 meters. Minus torque number 1 is acting at a distance of 0.4 meters with a force of 19.6 times 0.4 meters. Minus torque number 2 is what is left. It is 9.8 newtons at a distance of 0.2. Distance of 0.2. Okay. And if we add it all up, we subtract it all, we get negative 8.33 Newton meters. That negative just indicates it's opposite to the direction we chose as positive. So since we chose clockwise as positive, it means this is a torque 8.33 newtons, opposite to positive, so 8.33 Newton meters in the anti-clockwise direction or counterclockwise direction. So it's just going to be 8.33 Newton meters counterclockwise. Okay, and we can see that. Okay, we just worked it out. It's going to be counterclockwise. Okay, the sum of this torque is going to be counterclockwise. Okay. Now what happens if all those forces are just in equilibrium? This problem is going to be an introduction to our next section on equilibrium. Okay, so the next section deals with equilibrium. Let's deal with equilibrium. Okay, so this is problem number, I don't know what this one was. This was number 5, I think. Yes, this one was number 5. The problem we just did was number 5, so this would be number 6. Then our last problem on pure torque. Okay, the next problem will be on equilibrium. Okay, meaning sum of the torques are equal to 0, the net sum of the torque and the net forces are in equilibrium. Okay, so same situation as before, but in this case we are given two forces acting on this, one acting there and one there. In this case the forces are the weights of these blocks. Okay, this block has a force of 19.6 newtons acting perpendicular to the block. Well, this one has a force of 9.8 newtons. Now note, this is not drawn to scale. This is a distance of 0.4 meters, and this one a distance of, we don't know yet, we want the distance. Okay, so and they tell us that this situation is in equilibrium. It is in equilibrium. It is in equilibrium. Meaning that the torque, clockwise torque, is directly equal to the counterclockwise torque. So the clockwise torque is equal to the counterclockwise torque. The clockwise torque is the torque causing it to rotate clockwise, so it will be that one, the 9.8. So it's 9.8 newtons multiplied at a distance of 0.4 meters, which is equal to the force acting causing a counterclockwise torque, which is 19.6 newtons causing counterclockwise. So it's rotating in that direction counterclockwise, and its distance is unknown. Okay, the distance is unknown, d. Now let's solve for d. Okay, d will then be equal to 9.8 newtons multiplied by 0.4 meters divided by 19.6 newtons. That distance will then be 0.2 meters. Okay, that is the distance at which this force, 9.8 newtons, must act in order for it to bring about a distance, not a distance, a equilibrium, an equilibrium. And you can see, okay, that one is twice this force, so it acts at twice the distance, or at half the distance. Okay, this one is half that force, so it acts at twice that distance. Okay, the longer the distance from the fulcrum, the less force you need to apply. Okay? The closer the force is to the fulcrum, the more force you need to apply. Okay? That is all of our problems that we have on torque. Let's go to equilibrium. Okay, let's go to equilibrium, and then we're going to go do some more problems. Then we are done for today. Okay, so let's go to equilibrium. 14.4, the conditions for equilibrium. What are the conditions for equilibrium? Okay, 14.4, we've already established what equilibrium is. Okay? We have established what equilibrium is. Okay? Let's just go back and remind ourselves what equilibrium is. It's defined to be motion without rotational or linear acceleration. Okay, so it's motion without rotational or linear acceleration. Okay? That is equilibrium. So what are the conditions for equilibrium? These are the conditions of equilibrium. conditions of equilibrium. Let me see something here. I wonder you can still see my handwriting. The conditions of equilibrium. Where is this? Why is it so far? I'm just checking something here. The conditions of equilibrium. Let me just, I think I should switch on the ring light. Let me just see where it is. Just give me a moment, guys. So I can see clearly. Well, you guys can see clearly. I can see fine. Let me just see. Where's the switch to the ring light? Okay, there it is. I wonder if it's plugged in. It should be. Okay, there you have it. Now it has this a bunch of wires. Okay, that should be better than nothing, I guess. Let me just see, is it better now? Okay. Where were we? It's not that much better now. I wonder, wasn't it better if we just had it off? Or maybe I should move it that side. The conditions for equilibrium. Okay, then I'm going to switch off my face camera because it's going to reflect off me now. Okay, sorry, I did not see you, Timberletu. You asked, why did you use cos and not sine? Number 4, let's see number 4. Because I need to use, I wonder if you're still there, Timberletu. Sorry. Usually there's no one checking in. Okay. You have a question on number 4, why I used cos and not sine. Well, I needed the perpendicular component of this force, okay? And let me just see there. I'm going to type your answer. I needed to calculate the perpendicular component of the force. That is why I used cos and not sine. And it seems I got too late to answer. Sorry about that. Usually there is no one listening to me because, yeah. So, yeah. I needed to calculate the perpendicular component of the force. That's why I used number 4. At number 4 I used the usually there's no one now because usually when there is Timberletu, is that you who just joined? I don't know if you just joined. Anyway, that is why I used the cos, because I needed to calculate the perpendicular component of that force, and if I used sine, it will give me the horizontal component. But in this case, Timberletu, is that you who just joined? Can you just give me an indication if it's you? My current viewer, if you have any questions, I did here, I don't know if it's you who asked why I used cos here and not sine. Can you just indicate by means of yes or no? Is it you? My viewer, the current viewer there, can you just check, can you just indicate that you can hear me, first of all? In the chat, can you just type anything? Can you hear me? The viewer, can you hear me? Okay, the viewer that asked why I used cos and not sine, I assume you mean actual sine, so this is the sine tangent, that sine. Because you spelled it sine there, but that's fine, I know what you meant. I used sine because I needed this component of the force here. I needed this component, the vertical component. Well, the component of the force is perpendicular to the object, okay, acting perpendicular. Okay, so I needed this component of the force. Okay, and I used the cotangent. Okay, this is the angle, this is the right angle triangle, and this would be 60 degrees. So I needed to use cos if I wanted to get this. I needed to use the cos identity, trig identity, if I wanted to find this force here. Okay, the force acting perpendicular to this span. Okay, I hope that makes sense. Okay. Anyway, I'm going to continue. Conditions for equilibrium. I hope that makes sense. I needed a perpendicular component of the force. Now, conditions for equilibrium. Just put on my WhatsApp on. There are two conditions for equilibrium. Two conditions. Sorry, I missed your question a bit. Right? Sorry about that. But I hope it's clear now. Okay. There are two conditions for equilibrium. For a rigid body in equilibrium, unfortunately I only have so much screen space. So let me just focus on the chats. If they are, the viewer is gone again. But anyway, for rigid bodies, for a rigid body, meaning it's not bending, not rubbery, for a rigid body, in equilibrium, for a rigid body in equilibrium, so for a rigid body in equilibrium, the two conditions must hold. The following two conditions must hold. Okay. The net external force. Okay. I'm just going to write it in symbol form. The net external force. Okay. So the net external force must be equal to 0. The second condition is the net external torque. The net external torque must also be equal to 0. Those are the two conditions for equilibrium. Okay. I wonder if this light, is it helping at all? I don't know. Let me see. It makes things look even more darker. Let me open that window. It's getting darker for some reason here. Let's see now. Maybe now they'll have enough light. Okay, let me move the light source. Okay. Okay, that should be fine now. Anyway, you can just read off there. You can just follow in your notes as well. Now let's go to, I need to flip between multiple screens. So my viewer at the moment, can you just indicate that you can hear me? Just a simple yes or no. I'm going to wait and see if you can hear me. Just a simple yes or no, please. Okay. Seems the viewer doesn't want to interact at the moment. Okay. Let's look at this problem. Okay. It says here, number one, we often see people balancing a load on their head. Okay, this camera has moved. Sorry, I knocked the camera out of direction now. There we go. Let me just switch it off, rather. Trying to fix it. Okay. Okay, so we often see people balancing a load on their head. Okay, explain why the center of mass of the load needs to be directly above the person's neck vertebrae. That is obvious, okay? It needs to be directly above your vertebrae so you can balance it. So the amount of torque is zero, okay? Because there's the net external torque. If it's a little to the front, there's going to be an external torque towards the front, and if it's towards the back, it's going to be external torque towards the back, and both of those external torques will cause you to fall down, or cause it to fall down. If it's directly above your head, there is no net external torque, and the forces are balanced. Okay, it's in equilibrium if it's above your vertebrae, let's just say that. Okay, two children, this is what I want to get to. The other one you can reason out for yourself. Okay, two children, this is number two. Two children, there's no more questions. Push on opposite sides of a door during play. Okay, so there's a door. There is the hinges of this door. There is the door. So if we're looking at this door from above, okay, both push horizontally and perpendicular to the door. So they're pushing horizontally but perpendicular to the door. Okay, so the forces are perpendicular to the door. One child pushes with a force of 17.5 newtons. So one child pushes with a force of 17.5 newton at a distance of 0.6 meters. Okay, so at a distance of 0.6 meters. So that is 0.600 meters. So that is 0.6 meters from the hinges, and the second child pushes with at a distance of 0.4 meters. Okay, so the second child a distance 0.4 meters or somewhere there. Second child has a distance of 0.4 meters. 0.450 meters. The second child, distance of 0.450 meters. What force must the second child be pushing with? What force must the second child exert to keep the door from moving? That means this child here will cause a torque that is going to be counterclockwise, or the counterclockwise torque must equal the clockwise torque that the second child will bring about. Okay, so let's see. This is the first child, child number one, and this is child number two. Okay, the torque created by the force of child number one is going to be counterclockwise, or the torque created by the force of child number two is going to be clockwise in this drawing. Okay, so, and since it's in equilibrium, the sum of the torques must be equal to zero. That means that the clockwise torque must be equal to the counterclockwise torque. Okay, so we can work out the counterclockwise torque. It's just going to be 17.5 newtons multiplied by the distance of 0.600 meters, and then the clockwise torque is going to be the force F perpendicular that we don't know yet, multiplied by 0.450 meters, but we can then work out that force, and it's going to give you 23. That's what I got, 23.33 newtons. This force this child must exert is going to be 23.33 newtons, and we would expect it to be higher since he is closer to the hinge. And this is what the book got as well, 23.33 newtons, okay, of torque, of force, sorry. Okay. The next question. Let's go ahead. We're going to do one more problem on torque here, and then we'll move. Now here, safe physics. Okay, safe physics. Okay. Now, once we have established that the system is in static equilibrium, we practice safe physics. Okay. So what is safe physics? Okay. Safe physics refers to, it's an acronym referring to sketch, the axis, forces, and then the equations. Okay, S meaning sketch your scenario as you've just seen now. It helps to sketch whatever it is that you're doing. The axis, choose an appropriate axis of rotation. Identify all the forces acting in your body, and then solve the equations. Now see the lecture slides for examples from the textbook. Okay, we're going to do this example of the horse leaning against the wall with the rider on top of it, and then we will call it a day. We'll finish that. We'll be done with equilibrium problems there, because we need to move to the PHYV section. We've done a lot of torque, so now we just need to do some equilibrium problems. We'll do this one equilibrium problem. Problem number 2. Problem asks, suppose a horse, I need to move to PHYV questions as well. We're running out of time for this. At least we've covered most of, how to calculate torque, the important part. We've calculated equilibrium. Well, we've done some equilibrium problems. Okay. Now next we will do some problems on torque from the PHYV section. Okay. But let me just, I think I need to go take a drink of water now. Okay, this, I wonder if I should do it. Maybe let me just do this as well. Sorry, that is my calculator. I think I should go drink a little water now. before I come back to that problem and then do the PHYV after that. Just trying to get okay, I'll do that problem as well. Let me see. Okay, I'll do the problem of the horse leaning, and let's leave the drawbridge for now, so because we need to get to PHYB. But I'm gonna go drink some water. When I get back, we're going to do problem number 2 and number 3. Okay, you can look at it for now. This is the horse leaning against that wall. Okay, just give me 5 minutes. My throat is a bit raspy now. Let me just check, are there any questions yet? Okay, so I'm going to leave. Let me highlight the problem that we'll be doing. There's the problem. Highlight it. Doesn't matter, seem to highlight, but number 2 and number 3 we'll be doing now. Okay, the last problem number 2 and number 3. Okay, suppose a horse leans against the wall as in figure 9 on 9.30, 930. Okay, Calculate the force exerted on the wall, assuming that the horse is horizontal while using the data in the schematic representation of the situation. Okay. Note that the force exerted on the wall is equal in magnitude and opposite in direction to the force exerted on the horse, keeping it in equilibrium. The total mass of the horse and rider is 500 kilograms. So we need to calculate the force exerted on the wall, assuming that the force is horizontal. Okay? So we need to calculate the force exerted on the wall given the information there. Okay, there we have in figure 9.30b, we have that the center of mass, then we have the center of gravity, I think, the weight of the horse, the force of the wall on the horse, which acts at a distance of 1.2 meters, the height 1.4 meters, and then distance of 0.35 meters. Okay, so we need to calculate the force of the horse on the wall. Okay. No questions yet. Okay, there are 2 viewers. Okay, so now the torque on a rotating object depends on the force and the perpendicular distance from the force. Now we are given okay, what is it that we're given? We're given that the mass of the horse and the rider, the total mass of the horse and rider. We're given the total, that's number 1, we're given the total mass of the horse plus the rider. Okay, so we're given the total mass of the horse plus the rider. It's equal to 500 grams, 500 kilos. 500 kilos. If it's 500 grams, it's a really light horse, a really small horse and human. Okay, now the perpendicular distance from the center of mass. Okay, the perpendicular distance from the center of mass of the horse. Okay. So the perpendicular distance from the center of mass of the horse and the rider to the toe of the horse. Where is the drawing? There. Okay, so the perpendicular distance from the center of mass of the horse to the toe of the horse. Okay, so there, that 0.35 meters. Okay, so the distance, the perpendicular distance, let's just say perpendicular distance from the center of mass of the horse, perpendicular distance from the center of mass of the horse to the toe of the horse. So that distance is 0.35 meters. Okay, then what else are we given? Okay, the height. Okay, distance from the toe of the horse to the force exerted by the wall, to the force exerted by the wall. It's that 1.2 meters. Now I didn't need to write all of this in. Is that one? You could have just read it off from the the drawing, the schematic. Okay. Now the torque is, how do we calculate that force? Okay. Calculations. Okay, these are the calculations. Okay. The torque is equal to the distance multiplied by the perpendicular component of the force. That is torque. Okay. Now the torque is due to the torque. Now the toe of this horse is going to be its pivot point. Okay, so there, right there is going to be its pivot point. Okay, the distance from there to where its center of mass is 0.35. Okay, so let me draw it this way. Okay, so this is the pivot, this is the horse's toe, this is the distance, the pivot is here, this is the weight of the horse here, the weight of the horse acting here is its weight. This is the weight of the horse and the rider acting right here. The weight is acting the force, and that distance there we've established from the toe to its center of mass is 0.35 meters. Okay. Let me just redraw it. It is like this. This is the pivot, or its toe. This is in this case the pivot. There's the weight acting at that point, and the distance is 0.35 meters. There we have it. This is what is happening here. Okay, so a simple problem. Okay. So torque, the perpendicular component of the force, is nothing but the weight times the distance it's acting. Okay, the weight in this case is going to be 500 kilograms multiplied by 9,81 multiplied by the distance it's acting at 0.35, and that is going to give you a torque of 1715 Newton meters. Okay, the torque, that is the torque counterclockwise. That is the counterclockwise torque. Okay? That is the counterclockwise torque. Let me draw that situation because I saw. Let me make it rather neater. Okay, so this would be the pivot point, meaning this is the toe of the horse. The distance from the toe of the horse is 0.35. The distance from the toe of the horse to where the force is acting. The force in this case is nothing but the weight of the horse. So the distance from the pivot point, the toe, to where the weight is acting, which is the center of mass, is 0.35, and the weight in this case is 500 times 9,81 in this. So torque is nothing but the perpendicular component of the force times the distance, which is in this case, let me see if there are any questions yet. I missed the question earlier on. Okay, Timberletu, are you there now? Okay. Timberletu, can I just ask, are you there now? Okay, right now I'm calculating, this is the horse, this is the where the mass of the horse is acting, a distance about 0.35 meters away from the pivot point, which is the toe of the horse, and the perpendicular component of the force is just going to be the weight, and the distance is going to be that 0.35. So the weight in this case is going to be 500 kilograms multiplied by 9,81 meters per second squared. There's going to be a perpendicular component of the force, the component. Okay, so Timberlake, you're saying when we are dealing with conditions of equilibrium, I always fail to identify the component I have to use. You mean like the vertical? You need to be to use the component that is perpendicular to your force. Okay, not perpendicular to your force. You need to use the component of the force that is perpendicular to your line in which the force is being acted. Okay, in this case, this pivot, the toe of the horse is the pivot, while this line here is, well, I'm not gonna say it's the horse, but technically yes, that is consider it a beam. Like, it's easier to draw it this way. This is the toe of the horse. That is where the weight of the horse is acting. Okay, because we've done torque problems in this manner. Okay, so it'll be 500 times 0.3. Let me just finish this meters. I don't know, actually, you're saying it is when dealing with equilibrium, you always fail to identify the component you have to use. Like, can you be more specific? What component? Like the component of the force that you have to use. Okay, are you meaning that you're failing to identify, is it sine or is it cos? Okay, is that type of component? Okay? Which component of the force you have to use? The sine component of the cos component? Is that what you mean? Because that is the trend of our conversation so far. Me and your chat here. Let me just write here. Do you mean to say the sine, or first of all, tell me, do you understand, like earlier, why I use the cos? Let me just, I'm just going to give you the answer here, and then I'll get back to you. First of all, tell me, do you understand why earlier on I used the cos and not sine? I used cos because cos will give me the vertical component of that force, and we're always, not the vertical component, the perpendicular component of the force. We always use the perpendicular component of the force, meaning the component of the force that is perpendicular to the direction of the beam or whatever it is, the door. Okay. So let me just get this quickly. I had it written down. Let's see. Yeah, it is 1715 newtons meters, Newton meters. So that is the counterclockwise torque. There is a counterclockwise torque. Now, the torque at the toe of the horse due to the horizontal is the torque at the toe of the horse due to the horizontal. First of all, the torque is caused, this torque is caused by the weight of the horse. The one that we just worked out is caused by the weight of the horse. Okay. Now there's going to be a torque caused by the force. There are two forces. The weight of the horse that's going to cause the torque, and then the force of the wall is going to cause the torque. Okay. So let's calculate the torque calculated by the force of the wall. It's going to be force perpendicular multiplied by the distance. Okay. So still, in this case, the toe is going to be the pivot, horse, and then the force of the wall, F wall, it's going to act like this. It's going to cause a clockwise torque. Okay, let's see. So it's going to be that is how you, where F is the force of the wall. Which is going to have a clockwise torque. Okay. Now these two torques must be in equilibrium. The torque on the toe, I don't know why I say toe, because they're both around the toe. So torque, let's call this torque number 2 and torque number 1. they must be equal. Torque number 1 must be equal to torque number 2. Torque number 1 is 1715 Newton meters, while torque number 2 is the force on the wall multiplied by the distance that this force acts. Okay, so this force acts at a distance. What distance above the toe is 1.2 meters. Okay, so it acts 1.2 meters above the toe. Now, if the force on the wall, therefore, is then going to be equal to the torque that we just calculated, 1715 Newton meters divided by 1.2 meters, and that's going to give you the force on the wall. It is going to be 1429.17 newtons. That is going to be, sorry, I'm going to explain that again now quickly. Let me see if the letter is answered yet. Okay, no answers. But okay, so let's see. We have calculated, in this case, there are two torques. Okay, let me just try to clear up any confusion there might be here. Okay, there are two torques. Okay, the first torque is caused by the weight of this horse. Okay, W, that is force W. It's this situation here. Okay, so that is the first torque, and this torque is going this way, counterclockwise. Okay, this torque causes a counterclockwise torque. This force causes a counterclockwise torque, and this force of the weight actually acts at a distance of 0.3. The toes are the pivot point, by the way. This horse's toe here is the pivot point. Right there is the pivot point. And this force is acting at a distance of 0.35 away from the toe, because that's where the center of mass is. Okay, it's there, SG. That's where the weight is acting. Okay, it is 0.35. Okay, now if we calculate this counterclockwise torque, we have that the perpendicular component of the force, in this case the weight is acting perpendicular to that direction. It is going to have 500 grams times 9.8 is the weight, multiplied by 0.35, which is the distance at which this weight acts from the pivot point, and that's going to give you a torque of 1715 Newton meters counterclockwise. Okay, now this thing is in equilibrium, meaning that the clockwise torque must then be equal to the counterclockwise torque. Now the clockwise torque is caused by the force of the wall. Okay, the wall is pushing a distance of 1.2 meters above the pivot point, okay, which is the toes. Okay, and the wall is pushing a distance 1.2 meters, and it's going to cause a clockwise torque. Torque number 2 is going to be clockwise, torque number 1 is going to be counterclockwise. Okay, I hope that makes sense. Okay, now torque number 2 must be equal to torque number 1 because it is in equilibrium. Okay, it is in equilibrium. It is in equilibrium. Okay, that means that torque number 1 must be equal to torque number 2, which is just the force of the wall multiplied by 1.2 meters. Okay, and there we can work out the force of the wall by dividing the torque number 1 by the distance at which torque number 2 is acting, the force number 2 is acting, and then we have the force of the wall, okay, which is equal to, we want, and you can also write this as 1.43 times 10 to the 3 newtons, which is exactly what the answer in the book is. If you see there, that is what the answer in the book is. Okay, so we got the correct answer. Now number 3, I'm going to do number 3, and then I'm going to go, because we've been busy with FDV for the last hour and a half, I'm going to use the last half an hour to do PHYV, also some problems on torque. Okay, so the next part of this problem, calculate the magnitude and direction of the force on each foot of the horse. I wonder if I should do it or just leave it. Okay, let me just leave that and go to the PHYV. I might not have time to do the PHYV stuff. Okay, let me just, or should I do it in one? Let's see, how long is it? Where are my notes? How long It's quite involved, so let's try not to get into that. I need to do the PHYV. We've already cut heavily into the PHYV problems time. Okay, so let's do PHYV. This is this one. PHYV is Physics 101 for engineers. Question number 13 and 14. Tutorial 6, I think. Two of static equilibrium. That one there. You know the last preview. Where is it? Let me start, finish attempt. Now start a new preview. So not all done finish. I need a new preview. Of course I didn't fill all the in. I am only need to do question 13, 14 and 15 with you guys. Okay. The question 13, 14 and 15. That's why I'm only interested in those problems. Okay, so there we have a equilibrium problem, I think. Let me just get rid of this. Okay, there. Question number 13. No questions yet. The figure, where's my notes? Let me just get rid of this. Problems on the talk. My notes, question number 13. Okay. The figure shows a uniform horizontal beam. This beam has a length of 10 meters, a mass of 25 kilograms, and it is pivoted at a wall. Okay, so that beam is pivoted at a wall. Okay, and for some reason you are only seeing a part of his beam. I don't know, let me see. You guys are not seeing the complete picture. Let me. It's still lagging a bit. You guys are not seeing. I don't wonder why. It's not showing the complete thing. It is somehow. Why is it doing this? I have no idea why it's doing this. Okay, question number 14. It seems to be there's a problem here. It's not showing the complete drawing. I'm trying to fix this now. Let me see. It cuts it off here somewhere. Why is it doing that? Cuts off a whole section of this for some reason. Okay, thank you, Timbal, to you see that you understand it. Let me try to redraw. You need to calculate the tension in the cable. Let me just redraw this because I'm not going to struggle now for the next half an hour. For this, there's something wrong with. Let me just. I'm going to do something else now. Where was it now? Workbook. Questions. Okay. Let me do this. Okay. Path. No idea what that is. Now it's double screen. I just need one part of the screen in focus at a time. Okay, this is the question 13. I'm just trying to remove the one below that. But it refuses to go away. It refuses to go away, so bear with me. Let me just do this, cover it. Okay. Okay, question number 13. Let's see what it looks like. I'm going to have to fix this. Okay. Okay, question 13. The figure shows a uniform horizontal beam of length 10 meters of mass 25 kilograms that is pivoted at the wall. Okay. So here's the drawing. Horizontal beam, mass 10 meters. No, length 10 meters, mass 25 kilogram. It's pivoted at the wall, with its far end supported by a cable. Okay, so we have a cable here supporting this end, and and it makes an angle of 51 degrees with the horizontal. Okay, so let's try and draw what is happening here. So we have a pivot, we have a beam, of length 10 meters. This beam has a mass of 25 kilograms. Okay, and it is supported by a cable which makes an angle of 51 degrees with the normal. Okay, that's it. That's all we need. And now they say if a person of mass 60 kilograms stands 3 meters from the pivot, there's the pivot. So here's a person. Okay, that's my stick figure there. There's a person. This person stands 3 meters from the pivot. So 3 meters away from the pivot is a person. And this person has a mass of 60 kilograms. Now they're asking, what is the tension in the cable? So we need to find T. Okay, what is the tension in the cable? Okay. Obviously this is an equilibrium problem. First of all, the weight of the person can be determined as follows. Let's first determine the weight of the person. This person is 60 kilograms. So the weight of the person is equal to, let me just go to where there might be questions. Let's go to the weight. Okay, someone just asked the Teams link. I haven't set up the Teams link for this because I only set up when you guys ask for it. And it is almost our last problem, so I think it would be let me just set it up then. We're a bit late in the session, but I don't always set up the Teams link. I don't set up. By the way, you don't not going to need a Teams link for this King, but let me just go to. I set up a Teams link when there are people that want to use Teams. Otherwise, it just interferes with my streaming. but I'm going to set up the Teams. Now whoever, the person who asked for the Teams link, please now you have to tell me if you're going to be needing the Teams link, because I don't want to go now and say open up Teams and then have my thing buffer and then you're not using the Teams. Let me see, where's the student that asked for the Teams link? Caesar, okay, you asked for Teams. I'm going to set it up. Let's see what you need. Join. Now Caesar, you can just go to Outlook, and on your calendar you should have an invite already. Just go to the meeting. Okay, you should have it on your calendar. Okay, just go to your calendar and then check there for Yaba Physics. The Teams invite is already sent out to you. Okay, while I wait for Caesar to join me. Just go to your Outlook calendar, please, Caesar, and then you already have the invite for this. It's already there on your Friday. Just go to your calendar, and then for Friday, just check. You still don't see what? Just go to your calendar. You should have an invite in your Outlook. If you go to your emails, go to inbox. You'll see there, right on your right hand side, there should be a calendar icon. It is also on the left hand side. It's going to be just below the envelope. There's going to be a calendar. Go to your emails, Caesar. Just go to your emails. On your left hand side there are on your extreme left hand side there are a whole bunch of icons running right next to the left hand side. The second icon from the top, okay, is going to be an envelope, and then you have the calendar icon. If you go into the calendar icon, you can just go to today, 5 May, you'll see Yaba Physics. You should already have an invite for it.
Mr. Pullen, yeah.
Hi, Sisa.
Hi, sorry, I've
See,
been
you're joined. Let me just see if I can. Am I on Arnold's now? Can you hear me?
I can hear you. Okay. I've been on, what again? I've been refreshing on my Outlook.
Sisa, can you hear me?
Yeah, I can hear you.
Your mic is on, so you should be able to speak.
I can hear you.
Sisa, can you either type yes, you can hear me, or
I can hear you. I can hear you. Come on.
Sisa?
I can hear you.
I can see you in the meeting, but I cannot hear you.
I can hear you.
I think I may have inadvertently used Arnold. Oh, I've muted you. I need to. I'm gonna mute and then unmute everyone. Oh, it seems I am Arnold in this case. I wonder if you're still there. Just muted myself. And put the meeting. I'm just going to continue now with this problem until I set up my own, because I seem to be in Arnold's meetings. Anyway, I'm going to continue this problem because we're running out of time. Cesar, if you have a question, we're back. Can you just type it quickly in the chat? I don't know if your mic is working or what. I'm trying to switch on your mic remotely. Okay, made you a presenter. Yeah, your mic should be on now. If you have any questions, Cesar, now, please ask. If your mic is not working, you can use the chat. Okay, but while we're waiting for that, let's continue the problem. Mr. Caesar. Okay, anyway, where we with this problem, we just first need to find out the weight of this person here, because his weight is going to play a significant role in the tension there, because it's going to cause a downward force. Okay, so his weight is going to be m times g. His mass is 60 kilograms. G is 9,81. I always use 9,81. meters per second squared, and that is going to give me 588. 588. Oh, so you and Arnold can hear each other, but I can't hear either of you. Anyway, seems to be I'm locked into Arnold's. But anyway, it's 5,889 newtons. That's going to be the weight of this person. So this is not my Teams meeting, it's Arnold's, so he still has executive rights. Hi Arnold. Arnold, by the way, is the other tutor on this platform. Now the weight of the beam. Okay, now the weight of the beam, it's directly in the center of the beam, where its center of mass is. Now the weight of the beam is going to be similar to the weight of the person. Well, not exactly the same numerically, it's similar in how you calculate it. The weight of the beam was 25 kilograms. So let's go 25 kilograms multiplied by 9,81. That will give you 245,25 kilograms. That is, newtons. That's the two weights that you'll be using. Okay. I'm going to leave this meeting because it's interfering with my streaming. Okay, newtons. Oh, so now we want the tension. Okay, the tension in the cable. We have the weight of the person and the weight of the beam. The weight of the beam actually will be at 5 meters, while the weight of the person will be at 3 meters. Okay, so let's continue. Now let T, okay, the tension in the cable, let T there, the tension in the cable, let it be defined as the tension in the cable. Well, we've already noted that, sorry. T is the tension in the cable, okay. T denotes the tension in the cable, okay. We have the weight of this person acting at a distance 3 meters, and then at 5 meters we have the weight of the beam, okay, acting on, of course, this pivot point and the tension in the cable to keep it in equilibrium. Now this, if we do that, we can get T sine theta, in this case T sine 51, you can get the vertical component of the force, okay, the vertical component of the force, okay. T sine theta can be the vertical component of the force. Now, applying the equilibrium about that pivot point, so the equilibrium condition says that the net external equilibrium around the point should be 0, and the net external torque around the pivot point should be 0, and the net external forces around should be 0. Okay, this means that let's not take into account L. Okay, so T sine theta times the length of the beam. Okay, so the vertical component of the force, let's just work with the torques. Okay, this tension is going to cause a torque. Okay, it's going to cause a counterclockwise torque. Okay, the vertical component of this tension, okay, it's going to cause the counterclockwise torque. And how do we get the vertical component of this tension? It is just going to be T sine theta multiplied by, the length of the beam, not L, not 4, the length of the beam, that is L, okay, not 4. Okay, so T sine theta is just going to be the vertical component of the force of tension. Okay, so the vertical component of the force of tension. The force of tension is pulling this beam upwards. Okay, so the vertical component of this tension is just going to be T sine theta times the length of the beam, which in this case I have denoted as L. Okay, and that I choose this counterclockwise direction as positive, so everything else is going to be negative minus the weight of the person times the distance that that person is standing is going to be a negative torque, and also the beam is going to have a negative torque, so the weight of the beam times, now beam always is in the center of the center of mass. Okay, the weight of the beam acts at the center of the mass, so L over 2, which is 5 in this case. Okay, L in this case is 10. Now we have everything to work out, and they should all be equal to 0, by the way. That should all be equal to 0 because it is in equilibrium. Okay, now t sine theta, if we solve for, if we move everything to the right, we get that t is equal to, you can just move that over there, you get WP, the weight of the beam, times the distance that the weight of, the weight of the person times the distance at which the person's weight is acting on this beam, plus the weight of the beam, which is just acting at a distance halfway down the beam, divided by sine theta times the length of the beam. Now L you can just cancel, or you can just put it in as 10, okay, because we know the length of the beam is 10. Okay, if we plug in everything, okay, the weight of the person is 588, we just calculated it to be 5889, times the distance, the person is at a distance of 3 meters away, plus degrees. See that right there, multiplied by 10 meters, which is L. And if you find that, you work it out, you get the tension T equals to, you work that out, I have it here somewhere, it's going to be 0.38 times 10 to the 3 newtons, or just or approximately you can say it is 0.39 kilonewtons. Okay? It's 0.39 kilonewtons. Okay, and let's see for this question, is there, okay, how can you see or identify the pivot point? Okay, Timberlake, you ask, how can you see? Do you mean in this particular question or in previous questions? Because in this question, they tell you the pivot point is there. They tell you exactly where the pivot point is. Here they say, the figure shows a uniform horizontal beam, okay, that is pivoted at the wall. So this is the wall on the side, and then it is pivoted at the wall. That round circle there, that is the pivot point. Does that answer your question, Tebalete? You ask, how can you see or identify the pivot point? In this particular question, they tell you exactly where the pivot point is. Well, anyway, the answer is 0.39 kilonewtons. Let's see. 0.39 or 0.38, approximately 0.39. What was the original answer? 0.385 or 0.389. So this is C. Let's see. 0.38 kilonewtons is the correct one, because we got 0.385. You round it up, you get 0.389, but it is 0.38. If you do not round, you will get 0.38. But anyway, that is the way you do that question. Next problem. Tambalete, can you just indicate whether I've answered your question? You asked, how can you see or identify the pivot point? In that problem, it was given to you. Usually, if it's a drawing, you will easily identify the pivot point because they indicate it. They will always indicate the pivot point where it is, either in a drawing, or they will tell you it is to the wall, or it is in the middle, or the boxes are on either side of the pivot point. Something like that. They will indicate to you in the question where the pivot point is. or in the drawing they will indicate the pivot point. You must have the pivot point in order to answer these questions. Now I'm already past my time. Let's see. Okay, question number 14. It says, Angie says an object is in equilibrium. Angie says an object is in equilibrium if the net torque about the center of mass is 0. Okay. Robbie says that an object is in equilibrium if the sum of external forces is 0. Which one, if either, is correct? Okay, Angie says that an object is in equilibrium if the net torque about the center of mass is 0. They are both wrong. Okay, it is not the net torque or the the sum of the external forces is 0. Which one, if either, is correct? Okay, neither is correct. The net external force and the net external torque about any axis must be 0. So C, the answer C. Neither is correct. The net external force is just the definition of equilibrium. Net external force and the net external torque about any axis must be 0. Okay, now question number 15. John is carrying a shovel full of snow. The center of mass of the 3 kilogram of snow he is holding is 15 centimeters away from the end of the shovel. Okay, so John is carrying a shovel full of snow. The center of mass of 3 kilogram of snow he is holding is 15 centimeters from the end of the shovel. He is pushing down on the opposite end of the shovel with one hand and holding it up 30 centimeters from that end with its other hand. Ignore the mass of the shovel. Sarah says that his hand is pushing down on the shovel, must be exerting. Okay, so this is the situation. This is for number 15. Okay. This is how I understand it. This is the shovel. Okay. This is his hand holding it. And this is his other hand holding it. Okay. And this is the snow pile. Pile of snow. I'm drawing it from the side. Okay. Of course, you can picture it a shovel with snow at the front. One hand is holding it here, so this would be the pivot, while other hand is pushing here. This hand is pushing downwards, this one is holding upwards, that one is a force downward of the snow. Okay, so they say the center of mass of the 3 kilogram snow is 15 centimeters from the end of the shovel. So 15 centimeters from the end of the shovel, that's where the center of mass of the snow is. Okay, he is pushing down on the opposite end of the shovel with one hand, so he's pushing down on this end, holding it up 30 centimeters from that end with his other hand. Okay, so he's holding it here 30 centimeters. Ignore the mass of the shovel. Sarah says that his hand pushing down, so she says this hand here, this hand pushing down, must be exerting a greater force than the hand pushing up. Okay, this one is pushing it up or holding it up, and this one is pushing it down. James says it is just the reverse. Which one, if either, correct? Okay, which one is correct? In this case, James is correct because the hand pushing up, okay, must exert a force that equals the sum of the force of the hand pushing down and the weight of the snow. So that force is always greater. Okay, this force here, this force holding the shovel in place, this force pulling it upwards, must be greater than this force because it has to hold this force. It must be in balance with this force pushing downwards and the weight of the snow. So C. Anyway, the reason I'm going quickly is because I'm already past my time limit. Okay, I've done that. So everyone, enjoy your weekends. This is all we have for Yaba Physics this week. I will see you next week, Friday. Bye bye.